In this tutorial, we will be discussing thermodynamics and the equilibrium constant. Delta G is the change in free energy when pure reactants convert completely to pure products. KEQ is related to the reaction favorability. The product-favored systems have a KEQ greater than 1. Therefore, both delta G and KEQ are related to the reaction favorability. The larger the value of K, the more negative the value of delta G. KEQ is related to the reaction favorability, as delta G naught is equal to negative RT ln of KEQ. R is the 8.31 joules per Kelvin mole, and T is temperature in kelvins. So let's take a look at what the numbers mean. If K is greater than 1 and delta G is negative, it's spontaneously going to go towards the products. If K is equal to 1 and delta G is equal to 0, it's already at equilibrium. And if K is less than 1 while delta G is positive, it's not spontaneous. It's going to go back to the reactants. So let's do a practice problem with these. The delta G naught for the reaction N2O4 yields 2NO2 is positive 4.8 kilojoules. Let's think about that for a second. It's positive, so therefore it's not going to be spontaneous. Also, they gave us our information in kilojoules, and yet our R is 8.31 joules. So we need to convert this over. I'm going to go ahead and do that now so we don't forget. Calculate the K for the reaction at 25 degrees Celsius. They gave us our temperature in degrees Celsius and needs to be in Kelvin, so therefore I'm going to add 273 to it to make it 298 Kelvin. So delta G naught is 4800 negative 8.31 times the temperature of 298 ln of K. I can multiply these two together to give me negative 2476 ln of K. And this is still joules per mole. Alright, I can divide both sides by negative 2476. Our ln of K is then equal to negative 1.939. Alright, so we have a natural log of K. We need to get rid of that natural log. In order to do that, we need to take the second function of natural log. And if you look on your calculator, you'll see that the second function of that is e to the x. Natural log and e to the x cancel each other out. So we're going to take e to the x of both sides. So the natural log cancels out on the left-hand side, and we're going to take e to the x of negative 1.939. That gives us a K equal to 0.1439. Now, at the very start of this, I pointed out the fact that the delta G is positive, so therefore it's not spontaneous. You'll notice that K is less than 1, also indicating that it's not spontaneous. Alright, so what about if we're dealing with Q when it's not at equilibrium? If Q is less than K, then delta G must be negative, and therefore it's going to spontaneously go towards the products. If Q is equal to K, then delta G must equal to 0. The reaction is at equilibrium. Q is greater than K, that means that delta G must be positive, and therefore it's actually going to go towards the reactant. It's not spontaneous. We're going to go in the reverse reaction. So if Q is less than K, we're on this side and we're going to move towards the right. If Q is greater than K, we're on this side, we're going to move towards the left. And if they're equal to one another, it's in the middle at equilibrium. We're going to do one final example. Calculate the delta G. Notice that there's no little zero up here like there is here. That's because it's a non-standard condition. That's why you have a Q here instead of a K. Calculate delta G at 298 Kelvin for the following reaction under the given conditions. So we have delta G naught is equal to negative 71.2 kilojoules. We know that our R is in joules, so we need to convert that over. So that negative 71.2 becomes negative 71,200 joules. Alright, so we have Q. Before we get started, let's go ahead and solve for Q so that way we can just plug it in. So Q is equal to the products of a reactants, just like we've done for the equilibrium constants. Nitrogen dioxide is right here. It's 2.00. Because of this 2 in the equation, in the coefficients, it's going to be squared over the reactants. So NO is right here, it's 0.1. Because of this 2 here, that means it's squared. And then O2 is 0.1. And there's no coefficient there, so we don't do anything to that one. So we multiply this all out, and Q comes out to be 4,000. So now we can put that into our ln of Q. So delta G is equal to delta G naught, which is right here. We want the one in joules, plus R, which is 8.31, times the temperature, which is 298 Kelvin, times the ln of 4,000, the Q we just solved for. So it's negative 71,200 joules. If I put all this into my calculator, ln of 4,000, which comes out to be 8.294, times 298 times 8.31, I get 20,539. So if I add those two numbers together, I get a total of 50,661 joules for the delta G. And that's how you do Gibbs free energy without it being standard conditions.